So I'm the co-founder and CEO at Arcium, and what we're building, as you might be able to get from the title, is confidential computing based on multi-party computations. And today I want to explain a bit more about how we utilize MPC, how that differs from FHE techniques, and also dive a bit deeper into the techniques that we actually use in MPC, which funnily enough is somewhat homomorphic encryption. So it's very close to fully homomorphic encryption, but yeah, with a few differences. So let's start off with confidential computing in general, decentralized confidential computing. So our goal is to bring a transformative shift with whatever technology possible, both to the blockchain but also to the traditional computing space. And there's essentially a few desired properties that we want for decentralized confidential computing, and that's trustlessness, because prior confidential computing techniques required trust, and there's also autonomous execution. So we want the ability for data in use to be protected. We want the ability to have data in an encrypted, protected state and still be able to process this data, right? And we want to be able to do that in an autonomous way. We want that to be outsourceable to whatever structure, be it a network or whatever makes sense. And we want to get as close as possible to plain text execution times. I think that's a desire for everything computing to be as fast as possible, but here it matters significantly because every time we're building systems that also protect the individual, I think, with privacy, there's this imbalance that if there's faster solutions, then companies will use those faster solutions and not care about privacy technology as much. So there's this need for close to plain text execution times, and then we want scalability, and especially also scalability for real number computations, because that's what recent times with models and predictions and inference we want to be able to execute in a confidential computation. And so let's quickly run through some confidential computing technologies. The first one, trusted execution environments, right? So this, in our opinion, legacy technology, I would say, because it's dedicated hardware chips provided by trusted entities, which have some place in the systems that we are building, but solely relying on these kinds of technologies is really problematic due to a fundamentally flawed trust model, because there's just trust in supply chains, in many different attack vectors, and so it's really just ignoring a myriad of exploits, vulnerabilities, and attacks we've seen over the last years. So that's why it makes sense to fully focus in on purely cryptography-based systems or find hybrid solutions with trusted execution environments and cryptography-based solutions. What people tend to think could be also a technology as utilized for those systems are zero-knowledge proofs in the form of CK snarks or CK starks. The problem with these allowing basically a two-party interaction, one party, a prover, to prove the truth of some statement without having to reveal the statement itself to a verifier. So essentially the verification of information and execution over that information without disclosure, really is that we want to have this notion of execution over secrets in a different environment than where the secret originally came from. So the owner should not have to run those executions. We want autonomous execution. And for this, those primitives are not suitable as this core technology. I mean, zero-knowledge proofs are part of all cryptographic protocols almost, but really as this core technology, those really don't make sense. And that's why one arrives at fully homomorphic encryption, which I'm sure all of you are familiar with, and allows for this very interesting notion of this ability to operate over an encrypted representation and output another encrypted representation of data without having to touch the plain text itself. All operations can occur over the ciphertext, and that's exactly what we want to achieve with decentralized confidential computing. At the same time, there's these, so the homomorphism exists in relation to basically two operations. So additions and multiplications over whatever field one operates. So essentially the homomorphic encryption provides a ring structure where both addition and multiplication can be executed, and that's very great because with that NAND gates can essentially be represented, and with that any computation can be represented as well. The practical limitations, however, are extreme slowdowns, and they are very severe. So as I said at the beginning, what matters for these kinds of technologies is actual adoption. And when working with slowdowns for more complex operations, even many orders of magnitude above plain text execution, we need to find a way to be able to speed those things up. And I think there's tremendous research in the hardware acceleration department for fully homomorphic encryption, and I think we'll see amazing advancements on that front over the next couple of years. But what I really want to focus on in this talk is what's possible today to do efficiently, right? And another problem really is that in reality there's not this zero trust assumption, FHE implementation in decentralized confidential compute, because for things like selective disclosure, so the ability to reveal information about the plain text, there has to be some way of decrypting it, and that means the introduction of trust into those systems. And so the next technology really is secure multi-party computations. So secure multi-party computation allows a set of players to compute a shared function over distributed private data without having to share that data. So it's essentially a distributed witness across n players, and what's happening is that the players have secrets and they share those secrets. And for the sake of this presentation, this is the representation I pick for secret shared values. So the cornerstone of multi-party computations is this concept of secret sharing. And secret sharing is each of those players being in possession over data and taking that data, the secret, and splitting it into random secret shares. So blinded random secret shares that don't individually convey any information about the secret itself, but put together allow for a reconstruction of a secret. And so I think I actually need to skip to the next slide. We can think of this in a quite simple example. So we have Alice, Bob, and Charlie, each with their dedicated salaries A, B, and C. And the shared function that they want to compute is the average of their collective salaries without sharing their individual salaries. And so they start off by performing the secret sharing, which means each of the salaries can be represented as, in this case, additive shares, which with every single share essentially being a random value, not conveying any information about the sum itself. And so every player constructs those secret shares, and then they share them with each other. And so Alice ends up with 3 shares, Bob and Charlie, and everyone maintains one of the shares from their own secret value, and they receive one from each of the other players, right? And what's possible now is to perform local computations as every single player. And so they compute the sum. Alice, in this case, would compute the sum over her shares. Bob would do the same thing, and Charlie as well. And then at the end, we have a reconstruction. So we have different kinds of, we have mutated secret shares at the end, but by combining them back together, publicly opening them, we are able to gain knowledge about the average of their salaries without any of the players gaining knowledge of the individual salaries, right? And so that's a very simple example of a multi-party computation. But what's important is that secret sharing is this core principle. And what we utilize and what different kinds of multi-party computation protocols utilize is so-called semi or somewhat homomorphic encryption. And this is a concept that allows for a homomorphism just under one operation, right? And so where fully homomorphic encryption allowed for homomorphic additions and multiplications over that field, in semi-homomorphic encryption, only one of those operations, and in most cases the addition is homomorphic. And in FHE, the multiplication homomorphism usually is quite expensive because it adds noise to the ciphertext, and so bootstrapping operations or other protocol implementations are required to allow many multiplications to occur, and then over time that really adds up to the complexity of the operations. And so the principle here is really to say, okay, additions can be done cheaply, and so let's keep them homomorphic, and for multiplications, let's find a different protocol. And so the general constraints with this approach is that there's a trust model on the protocol level itself involved, so either a dishonest or honest majority trust model. And as I said earlier, that's still the same case for most decentralized FHE implementations, because you want selective disclosure to be possible in order to reveal information if you want some settlement back on a public ledger. And at the same time, so for us personally, at Arcium, we have a protocol with the dishonest majority trust assumption, which means out of a set of n players, there has to be one honest player, one player not maliciously collaborating with the others to undermine confidentiality. And in an open environment where anyone can join such a computational network and become an honest player, this is a reasonable trust assumption. But there's differences in performance by default for honest majority and dishonest majority protocols, but the tweaks that I'll show you in a second for dishonest majority protocols really allows them to even be quite efficient. And scalability with the number of players is also a concern, where I'll show you an optimization technique in a second. But let's start. Let's skip that again. So essentially, what we're working with are MPC protocols in the pre-processing model, which means that the entire computation is being split into 2 parts: a pre-processing phase and an online phase. And the pre-processing phase is completely independent of the circuit that's being executed and the inputs that are being used. And the pre-processing phase is being used to outsource workload from the so-called online phase into a phase that happens up front. And it's being used to generate data that is being consumed in this online phase, so-called beaver triplets, which are correlated randomness, which we'll see in a second. And then the online phase is using this data and is able to run computation close to plain text execution. And so additions in such a setting are homomorphic. So that means that if we have two values that are again represented as secret shared values, everyone can simply add the share that they're holding to the share of the other value, and they receive the corresponding value. Constants can also be added in the same way, and constants can also be multiplied in the same way. Now for the actual multiplication of two secret shared values, we utilize those beaver triplets. And beaver triplets are just two values, A and B, which are random values, and a value C, which is the product of those values. So that's correlated randomness. Essentially 3 random values, but C and A and B are correlated to each other. And this data is generated in the pre-processing that can either be generated completely trustless or with a so-called trusted dealer. We won't focus on that at this point in time. It's just, we can just imagine that we have this correlated randomness available and one beaver triplet for every single multiplication that has been generated in the past. And what's now being done is 2 values are being computed. A secretly shared value D and a secretly shared value E. And X and Y are the values of which we want to compute the product. And you'll see in a second what we can do now. So those values are collectively being revealed amongst all the players using communication. And then we can compute this final product. So we take this pre-computed product, this multiplication that has happened in the past, together with a cryptographic proof that C is actually correlated to A and B. And then we use that pre-computed product and we adjust it to the secrets that we actually want to compute the product of, right? So we adjust it by adding the products with those two sums that we previously computed and publicly revealed the values of. And then at the end, we need to correct by those values again. And so what we're able to do with this protocol is we can do the heavy lifting actually in the pre-processing phase. So the entire heavy lifting of running those multiplications can be done up front. And we have those proofs that those values actually are correlated in this product fashion. And then we can get this very fast online phase, which is this actual execution, which comes with good scalability, communication-wise, but still not ideal scalability because it's still linear with the number of players involved for every single multiplication gate. So another optimization we can make use of is packet secret sharing. And so if we take traditional Shamir secret sharing, there we have secrets represented as a set of n shares with a threshold by using polynomial interpolation. And packed Shamir secret sharing allows us to use a vector of secrets in one polynomial. And what we're able to do is per communication round, we take, instead of just individual secret shared values, we take those polynomials as secret shared values, which themselves represent this vector of secrets. And so with this setup, we're in certain scenarios able to drop the communication overhead to almost constant time. So in any case, it becomes sublinear, but of course, that amortization really depends on also having to construct those polynomials because they depend on the concrete input values of the online phase. But still, with this setup, we also can more heavily utilize hardware acceleration because we have those vectorized operations, and it's really those large batches essentially of multiplications happening at the same time, and then less network communication, because at the end of the day, that's still the latency that we're working with. So the most latency penalty we also see with this somewhat homomorphic encryption system is based on network communication. But yeah, those are a few optimizations that we have essentially in our protocol. And FHE can also be used inside of the pre-processing phase, but in most cases, oblivious transfers will be faster in order to generate those beaver triplets. But yeah, that's the core technology that we're using, and so I think I can skip through some of that. But yeah, essentially we used a set of protocols in combination with dishonest majority trust assumption, yeah, there's different more things that can be added to the pre-processing phase. In our case, we added this ability to cryptographically identify misbehavior during the computation without adding additional complexity to the online phase. So if the computation fails, we can pinpoint which player shared some invalid secret share, and we can punish them. And that allows us to, with Arcium, build a stateless computational network that uses existing blockchains as consensus and state layers. Yeah, I think that should be most of it. We also have some optimizations for AI, but yeah, let's leave it at that.
All right, thank you. Any questions?
Thanks. What's the stage of your project today, and what kinds of use cases are you going after?
So right now we're planning to move into private testnet. So our computation network should go live within the next 2 months, fingers crossed. And so use case-wise, what's really the focus for us is to just optimize computations and offer this permissionless computation network that can be used both from a blockchain, but also can be used by enterprises, because it's just this computational network, and confidential smart contract execution is just something that gets compiled down to what this network is capable of executing. And so there's both the use cases on the blockchain, on the crypto native side of things, but also I think even more importantly in real life. So to be able to, with something that I wasn't able to touch on with the real number arithmetic optimizations, for example, to be able to run federated learning, so machine learning over distributed data sets without anyone having to share those data sets with each other, while still being able to run this collaborative model. So it's on the one hand wanting to provide collaboration, and on the other hand just using the technology also as a secure execution environment, because you don't have to collaborate, you can also use it as an execution environment with some trust assumption involved if you're not actually part of the computation, but still as minimized as possible trust assumption. Yeah.
All right. Any other questions? All right. Oh, okay. Follow up.
So will you build your own private networks or crowdsource infrastructure?
Yes, exactly. So in our network, anyone can run their own node and can provide computing power to this confidential network. And the network itself really is this open network. And if someone wants to run confidential computations, they can pick whatever nodes they want They can create a cluster of those nodes. So they can pick 2 nodes, they can pick 100 nodes to run their computations, doesn't matter. Or they create 1 node themselves and someone else has one and they create this permissioned environment. Yeah.
I'm just really wondering, what's gonna be the business model for this? How you're planning to generate revenue?
It's a peer-to-peer computational network. So there's no intermediary in between. We're not some intermediary that tries to get a fee or something. It's really this open infrastructure that we're building. Yeah.
So I took a look. One part of the network's value proposition is also the parallelization. Could you talk a little bit more on that, like what exactly that is?
Yeah, sure. So the parallelization really arises from being stateless, for one, right? So the network doesn't have to operate over some shared state. It can have a cluster that does computations for me and different clusters that do computations for you. And it can even be one node across all of those clusters doing those computations in parallel, because no computation depends sequentially by default on the execution of some other one. So it's not a blockchain. And on top of that, we can have different complexity for the computation duration. And the only thing that matters at any given point in time is speed of light and network bandwidth, because I mean we are able to bring down communication overhead significantly with those techniques, but still that's the limiting factor at the end of the day, network communication at a point in time. But until the bandwidth of a node is completely used, everything it can execute as much as hardware allows in parallel. Yeah.
So this is your separate own network, like you said. Would this make sense as an L2 on Ethereum or something?
So it's dedicated network, and we plug into existing L1s, L2s, and we call them consensus state layers. So you can access this network from whatever place, but we've consciously not gone down the road of building an L2, simply because for us it really should be this stateless network, and if it has state, it should actually just be secret shares. It should not be some smart contract state and account state. It should really be optimized for those computations, because as an L2 you wouldn't be able to have this sort of parallelization, and so we can have those blockchains as access points, essentially.
All right, well, let's thank our speaker again.